I'd like to welcome Professor Bhavik Bakshi, who holds the Wrigley Professorship at Arizona State University, with appointments in the School for Engineering of Matter, Transport, and Energy, School of Sustainability, and School of Complex Adaptive Systems. He's also the Richard M. Morrow Professor Emeritus in the Department of Chemical and Biomolecular Engineering at The Ohio State University. He's been at Arizona State for about a year now. His research is developing systematic methods to ensure that engineering enables an effective transformation towards sustainability. He has numerous awards. I'll highlight one in particular. He received just last year the AIChE CAS Division Computing in Chemical Engineering Award, and we're honoring him with this webinar presentation today to talk about his work in sustainability. Professor Bakshi received his Bachelor of Chemical Engineering degree from the Institute of Chemical Technology in Mumbai, the Master's in Chemical Engineering Practice, and Ph.D. in Chemical Engineering from MIT, with a minor in Technology and Environmental Policy through courses and research conducted at Harvard University's Kennedy School of Government. So with that, let's go ahead and welcome Professor Bakshi, and I'll turn the time over to him.
Okay, thank you very much, John, for the kind introduction and this opportunity for organizing this webinar. And thank you to all of you who are participating live and those who are watching it, later on. So what I want to do is to give you a little bit of a perspective. And as you can see from the title, the claim that I'm making is that the future of process systems engineering is sustainability. So, when you get an award like this, I guess people expect you to have some type of perspective. Hopefully I do too. At least I'm going to try and give you my own biased view on what I think and why I think the future of process systems engineering is and needs to be sustainability. So, as you know, PSC has a long history of contributions that have transformed the chemicals industry. And Roger Sargent, Professor Roger Sargent, who was at Imperial, is given the credit for being the father of the field many decades ago. But traditionally, PSC has been motivated by this need to improve profitability, which is certainly a good driver. It's been a very effective driver, and it's resulted in improvements in engineering design, in process control, in process operations, and many other areas. So as you know, we have developed a large number of methods and tools that are very widely used. Several of them are commercialized and thriving companies. But the past was driven primarily by profitability. My argument, what I'd like to pose, is that the future of PSC will be driven by sustainability. Note that profitability is a part of sustainability, but it's not the only component in sustainability. Sustainability requires economic feasibility, ecological viability, and social desirability. All of those three things need to come together when we talk about sustainability. So in my presentation, what I want to do is start out with providing you with a history of industry and the environment. How has the attitude and the approach of industry and the environment changed over the last many decades? It has changed basically, as I'll describe, from treating the environment as a threat, or rather environmental protection as a threat, to treating it as an opportunity, to now it kind of seeming like an existential crisis for industry. I'll also talk about how has process systems engineering evolved over the decades, moving from the focus on equipment to enterprise and supply chains, and also the other direction from equipment to agglomerates and molecules and atomic levels. And what I'll argue is that it needs to expand, or it needs to continue its expansion to incorporate the economy, society, and biosphere in the push towards sustainability. I'll also, talk about some of the challenges and opportunities that I believe PSC has from the sustainability viewpoint. And I'll show you one set of results and some work that we have been doing on transitioning to a net zero emissions chemicals and materials industry, and also give a glimpse of some work on techno-ecological synergy that we have been working on. So in this presentation, I've deliberately kept a description of our work a little bit less than I would otherwise, but rather focus more on providing that big picture perspective and view towards the future from my vantage point. So let me start out by talking about industry and the environment. Just provide you a little bit of a historical view of where we have been. How has the relationship between industry and the environment changed over the decades? So before the 1980s, in general, if you look at this diagram over here, the perspective was more of a win-lose perspective. In other words, the thinking was that if you wanted to make more money, go from A to B, then the environmental impact had to go up. Okay, so environmental protection was treated mostly as a necessary evil and a temporary nuisance. And even the impact of industrial emissions was, companies had been unwilling to accept the negative impacts. So this is a statement taken from a newspaper article that appeared in the 70s. And it said related to a spill that killed a large number of fish, that there was no conclusive scientific evidence that pesticides damage the ecosystem, and that its role in increasing food production was a proud example of its contribution to progress. So, the attitude was very different. At that time, there were, in the US and many other parts of the world, there were some big environmental disasters. One that is shown in this picture is a fire on the Cuyahoga River near Cleveland, Ohio, in 1969. There were also documented problems with pesticides, the book called Silent Spring that Rachel Carson wrote, and so on. So with all of these negative impacts, being known gradually, particularly since the 1980s, the perspective in industry changed from that win-lose perspective to a win-win perspective, where the thinking was that if we were to reduce environmental impact, so go from point A to point B, point D rather, you could reduce environmental impact and increase profitability. So a classic article on this was written by Michael Porter, who is at the Harvard Business School. So he wrote this article in the Harvard Business Review, where he argued that environmental protection was not a threat to the business enterprise, but rather an opportunity. So that was sort of an approach, and a lot of companies actually showed that this was possible. But it required innovation and creativity. So the development of new products, new ideas, and so on, that showed that, if you found solutions that were economically better and environmentally better, that would be a win-win approach, and that was indeed possible. There are many examples of such innovations, and one that I will mention are, say, gas electric, hybrid engines that Toyota developed a few decades ago now. Many examples of this type come from the process intensification domain that is closer to chemical engineering. So gradually, people found that win-win situations are not always possible. So, there is really a practical perspective, which is a strategic perspective, where there is win-lose in the short term. So with innovation, you can move from the current win-lose curve, this one over here, from point A. With innovation, you can move to point D. And then for that new technology, you have another win-lose curve. So, you basically need to constantly innovate and update yourself and keep finding these opportunities that are win-win, and then managing the win-lose scenarios that will also be present in the shorter run. Over the decades since this perspective evolved, if we look at the relationship between industry and the environment today, it is one of environmental pledges. So here are some headlines and a statement on the left from Dow Chemical's sustainability targets about industry reaching net zero greenhouse gas emissions by 2040, 2050, and thereabouts. So most of the large companies have pledged to get to net zero greenhouse gas emissions. And Dow Chemical, as you can see, and I'm not going to read the whole thing, they're also projecting that by 2050, Dow intends to be carbon neutral, scopes 1, 2, and 3, plus product benefits. So that's the entire life cycle of all of Dow's products. They're saying will have net zero emissions by 2050. That is about 25 years from now. The reason for this push towards net zero is obviously something that I think is very well known, and I'm not going to get into that in any detail. But climate change, particularly the contribution of the chemicals and materials industry, I will use this acronym CMI to represent that. The chemicals and materials industry, which includes chemicals, metals, cement, iron and steel, etc., is about 30%, okay, as shown by this yellow region. And the indirect role or contribution to greenhouse gas emissions from the chemicals and materials industry is as large as 70%, meaning that chemical and materials industry products can directly or indirectly influence 70% of greenhouse gas emissions, which is obviously substantial. The other type of pledges that are increasingly common are related to plastics. There is the Global Plastics Pact and the US Plastics Pact, which has aimed to list all of the problematic plastics, transfer to reusable, recyclable, compostable plastics, and move to even bio-based plastics and so on. And the timeline here is pretty short, 2025, which is next year. Dow Chemical, I'm picking on Dow because they are exemplary in terms of their efforts, in my opinion. But many other companies most other companies in this business have similar goals. But in Dow's case, very similar. They want to go to a circular and renewable economy, by 2030. Reason for this is plastics pollution. Again, I don't think this needs any introduction. There are islands of plastics in the Pacific Ocean, and you cannot escape plastics on any beach anywhere on the planet today. The third area is that of becoming nature positive. Biodiversity loss is a huge problem, and there are pledges that are increasingly being made by nations and corporations to become nature positive. So rather than continuing this decrease in biodiversity, the gray line would be the business as usual case. We want to turn this around and get to net positive by 2030 and full recovery of the original level of ecological systems and biodiversity by 2050. Very aggressive, ambitious goal over here, but companies are signing on to these kinds of pledges as well. And the reason for this is that there is a substantial loss of biodiversity, which is essential for sustaining life on Earth. Nature provides services worth an estimated $125 trillion per year. Out of 23 ecosystem services, 16 are degraded. And this shows the loss of biodiversity along the world or across the world. This is the average for the world and various regions that you can see in all the parts of the world. And the story is basically not very different. Renewable energy is increasing threat to biodiversity potentially because of the large requirement for land use and materials intensity. So we do need to be very careful in expanding our use of renewable energy, that we don't end up making the biodiversity problem worse, because what we really need to do is to make it much better than what it is at this point. So with this background, then why is sustainability the future of PSE? As I told you in the previous slides, most corporations and nations have made substantial pledges towards sustainability. So why do we need PSE to focus so much more on sustainability, which is basically what I'm arguing in this presentation? The reason for that, going back to the same pledges, is that yes, companies have made pledges to get to net zero emissions. I showed you this slide earlier. But at the same time, there are other headlines and other reports out there that are showing that some of the biggest companies are failing on their own climate pledges. Making a pledge is one thing. Getting there in a manner that doesn't break the bank and is actually sustainable is a whole other matter. And today, we don't have systematic methods, models, and tools to guide this transition. Same story with plastics. Okay, I showed this slide again. Here also, many of the targets are going to get missed. Again, very difficult problem. So in my opinion, PSC must focus on sustainability. Even though these pledges are there, doesn't mean the pledges are going to be met. Environmental degradation constitutes an existential crisis for industry. Some say for even chemical engineering and chemistry and those sorts of areas, because the younger people seem to be less attracted to work in this field that doesn't exactly have a very squeaky clean type of reputation right now. Systems approaches are essential for meeting corporate pledges. Okay. Previously, meaning if you go back 25 years ago or longer, which is roughly when I started working in this area, at that time, the interest in sustainability and engineering was mainly from many nonprofits. It was mostly environmental science work, and there were a few other crazy people, myself included, who were working in this sort of area, many, many years ago. But today, the landscape is quite different. Industry is today asking for the expertise. Jobs are available in this area and they are likely to grow. And importantly, there are many important and interesting research challenges that our community can, and in my opinion, must address. And later could be too late. Okay, so particularly for the younger generation, right? This is the challenge of your lifetime. If you're not going to be spending time trying to address this, what else are you going to do? Because now is the time. So switching gears slightly towards the history of PSC and the environment. So traditionally, PSC, as I mentioned earlier, has focused on the equipment scale, gone up to the process scale, and then gone further to larger scales to the enterprise and the supply chain. And also the smaller scales going to agglomerates and molecules and atoms, the smaller scales going into, design of molecules, design of products, those sorts of things. Larger scale going to planning and scheduling and supply chain management types of approaches. So you've seen this kind of a diagram it's quite a popular diagram that I think Wolfgang Marquardt gets credit for developing this originally. And Art Westerberg and Ignacio Grossman wrote a perspective many years ago where also they showed a similar diagram. The focus of PSC has been on, as I said earlier, profitability. The emphasis has been on energy efficiency, reducing waste. Gradually, we have started including life cycle impact. But what we need to do is to continue that expansion to the scale of the entire economy, all of society, and the entire global biosphere. This expansion has already started, and this is what, in my opinion, needs to continue. So the big questions that we face today, right? And this is we meaning people in PSC, but overall, all of industry, the world. Is it possible for industry or chemicals and materials industry specifically to get to net zero emissions while being profitable, ecologically safe? By that, I mean respecting nature's capacity, socially just, being equitable and so on, and resilient. Is this possible? There are lots of alternatives and lots of new technologies, new ideas that are being developed. Okay, a lot of reductionist research that is claiming to contribute to sustainability, is going on in areas like renewable energy, chemical recycling, carbon capture, utilization and storage, electrification of industry, nature-based solutions, economic policies and behavioral changes and so on. So what will be their role in getting to this net zero emissions future that industry has been pledging it's going to get to within less than 3 decades? How should this transition to net zero be executed? Which alternatives should industry and government focus on developing? Where should they be putting the money? What should you as a researcher focus on? What are those emerging areas and frontiers that are likely to accelerate and have opportunities for fundamental and groundbreaking contributions? What will be the effect of a changing climate in the meantime? As this transition is implemented, the climate is also changing in parallel. And how can societal behavior be influenced? Also, very importantly, is it possible to come up with solutions that are inherently sustainable, quote unquote, sustainable by design, just as we have solutions that are safer or safe, by design, can we come up with products and process systems that are sustainable by design? What is the method that would give us those kinds of solutions? So there are a whole bunch of opportunities and challenges, for the foreseeable future, in terms of answering these kinds of questions. So the opportunity, I think, that is there, I think it's a rare opportunity for industry and everybody, who can help in this journey, to simultaneously capture market share, enhance competitiveness, improve environmental quality, and meet societal needs. So it's a win-win-win opportunity that industry, nations, and overall society has today, if we do it right. Lots of challenges, needless to say. Every alternative involves trade-offs between economic, environmental, and social aspects. We have to be very careful we don't end up shifting the burden across space, time, impact, categories, and disciplines. We may solve climate change, but if that results in more biodiversity loss, that will make the overall situation potentially worse. Okay? We improve efficiency, but if efficiency encourages consumption, that will also make things worse. So we have to be very careful and make sure that this burden shifting is not the outcome of our activities. Of course, we need alternatives. We need a lot of new ideas, new technologies, new policies, human behavioral changes, consumer behavioral changes, etc. And this whole system involves complex dynamics, lots of nonlinearities, and deep uncertainties. So the research agenda is long. Two broad things I think that PSE needs to focus on, and I think can make major contributions is in developing systematic methods, models, and tools to guide the transition to net zero, nature positive, and people positive engineering. And of course, we have been good at ensuring theoretical rigor and practical relevance. We need to maintain that. But for this, we will need to collaborate with the stakeholders much more than we have done in the past, because the stakeholders are not just other engineers, but it's likely to be government and society at large. So let me now, talk a little bit, about this, framework that we have been developing for making progress toward net zero, toward a net zero emissions chemicals and materials industry. And what I'll do is I'll use this framework to very quickly show the kind of work that can be done and that is being done, for meeting this kind of a goal. And then use that to identify where the PSE opportunities are for, for all of the steps that I'm showing in this framework. Okay, and I'm going to go through this relatively quickly. A lot of the results I'm going to show you are already published, but the intention is to give you that big picture perspective and hopefully motivate you and others, to do more research in this domain. So the framework is, we want to get to net zero. So we start out with a model of the current industry, right? We evaluate for the current industry, what are the trade-offs, economic, environmental, social. Our goal of, say, net zero emissions, is it being met? Well, with the current industry, the answer is no. So if it is not being met, then we have to identify improvement opportunities. And then to actually get that improvement done, we need to focus on innovation. How do we develop new ideas and new methods, new technologies, to do the improvement, and then update the CMI model with these innovations and repeat. Okay, and the approach that we are taking is we include enough innovations eventually that we are able to meet our goal of getting to, say, net zero emissions, or it could be nature positive, decisions, or whatever your sustainability goal is. Once you are in a position to meet the goal, then we try to develop a roadmap. We have future innovations that are included typically in our model right now, because that's the way we can get to meeting our goal. So how do we actually get from now to net zero, let us say, by 2050? We want to look at net zero emissions, but keep in mind, we also want to focus on nature positive decisions and people positive decisions. Those are all of the things that need to be incorporated. My focus mainly is going to be a net zero right now. So I'm going to use an example of grocery bags. It's a simple problem, and data is available for that, and something that all of us, I think, can relate to. So the question here is what type of grocery bag, is going to give us net zero emissions. Okay. We are focusing mainly on these plastic bags, a single use or few uses, high density polyethylene, low density polyethylene, polypropylene, polylactic acid, and paper. Those are the bags that we are considering. So, we have to consider the entire system. We need to consider the manufacturing of these bags, but we also need to consider the upstream life cycle and the economy within which the life cycle resides. We need to consider the use of the bags by households. What will the households do with it? Will they litter and put it into the environment? Will they put them into the trash bin or the recycling facility? And from there, will it go to a landfill, to pyrolysis, incineration, or to various types of recycling, mechanical, chemical, and other recycling facilities? Or some bags could potentially be composted. Just with, for this small system, there are a lot of alternatives, approximately 120 in this case. And each combination has different circularity, different environmental impact, and different cost. So even for this small problem, the question is, what is the best pathway? And is that pathway going to give us net zero emissions? And if not, how do we innovate for circularity? So those are the questions that I want to address over here with the help of this example. So it involves solving an optimization problem. I'm not going to get into details of this. Our community is very good at formulating and solving these types of problems. But, there is a life cycle model that goes into it. Consumer requirements are going in. Physical-chemical governing equations are in here. And there's a whole bunch of constraints that are involved in this optimization problem. So the results we get is with the currently available technologies, so these are the technologies that are available in the market today. The results are summarized on this diagram over here. So the y-axis is circularity index. Circularity index is being defined as the monetary value of recycling divided by the monetary value of the original materials that we are consuming. Carbon footprint is what is shown on the x-axis over here. It's a life cycle emission of greenhouse gases in carbon dioxide equivalents. So, the size and the color of the circles indicates cost. Smaller the circle, less the cost. Okay. So we can see that the cheapest solutions are right here, that's around, a carbon footprint of about 3 units and a pretty low circularity of close to 0. Okay, so the current technology is quite cheap, but it is not circular. Most of the material is just being, sent to landfills. Okay, circularity rates are very small. 14, 15% is like the highest that one tends to see these days. This is a US-based study. So we cannot achieve net zero emissions. This is the net zero emissions line. The red line is zero emissions, and we are nowhere close to it currently. So we cannot achieve net zero emissions. Circularity index at the most is 50%, but you see it starts becoming quite expensive. If we do more recycling and better segregation, etc., it starts becoming expensive. So, and the carbon footprint also increases. So circular economy with the current grocery bags is actually not a good idea. Okay, because it will increase cost and it will increase environmental impact. So what is to be done with the current grocery bags if you're interested in net zero emissions? The answer is don't use any of these single-use types of grocery bags today because none of them are any good. Okay, better to carry your own bag and a cloth bag and use it typically at least several hundred times. Okay, for the impact to be normalized per use. So, but there is lots of new technology that is being developed. There is renewable energy available. So what if we switch, to renewable energy? So in this case, we have added renewable energy. And these are the results we get for that. Same type of figure. You see most of the energy now is coming from solar, but the resources are still coming from fossil. And there is some recycled polyethylene that is also being included. Lowest cost solution, you can see over here, it has a lower carbon footprint, but circularity is still close to 0. You want to increase circularity, you end up with more carbon footprint and more cost. And you still cannot get to net zero. You're doing better than before, but you're still not at net zero. Okay, so renewable energy alone is not going to cut it, at least for these grocery bags problem. For most chemical processes, renewable energy alone is not going to do the job of getting to net zero emissions and of meeting the plastics pact. So we need more advances. So what if, there's a lot of new technology that is being developed. Much of it is at a very low readiness level, but what if it became available? Okay. Then what kind of scenario would we end up with? The results are shown in this slide. You can see now these dots represent, a large number of emerging eco-innovations, including many chemical recycling methods, better waste management and segregation methods, better materials. Excuse me. And you can see now we can get to net zero emissions, actually. It is going to cost us more, but you can increase circularity while decreasing the carbon footprint. That becomes possible finally. Okay. We can even go to net negative emissions if we're willing to spend more money, according to our current analysis. So with future technology, it seems like for grocery bags, we would be able to get to a net zero emissions future. So now we need to figure out a roadmap. Okay, how do we actually get there? Today, our situation is not that great for grocery bags, but in the future, it is possible. Let's say we want to get to net zero grocery bags by 2050. What is the plan? What is the roadmap for that? That also involves a large, more complicated multi-period planning problem, which is shown over here. Again, I'm not going to go into the details except to say that it's a multi-period problem. We are using continuous time Markov chains to approximate the evolution of technologies. There is a climate change model that is also connected in here. It's an integrated assessment model. There is a target for climate change and the US Plastics Pact. And this work is published in the May issue of AIChE journal. It's the cover article in the current issue, in case you are interested. The types of results we get are shown over here for these bags. This is showing over time, you see, going up to 2055. This is the current technology. Slowly, we would switch to pyrolysis of low-density polyethylene. That switch is already happening. In the future, we expect linear alkyl aromatics from polyethylene to become available as a technology. And then eventually, polylactic acid alkaline hydrolysis will become available. Greenhouse gas emissions, according to our model, are expected to go down and eventually get to net zero with these technology changes. And circularity is expected to increase and meet easily the Global Plastics Pact by 2050. So these are the kinds of results that are possible to get for using this net zero framework for at least grocery bags. But it's only grocery bags, and it's a very simple problem. We need to do this for the entire industry, every product virtually, every company, right? Every reaction pathway, every life cycle. So there are a lot of opportunities, I think, for process systems engineering, and there is a need for PSC techniques and tools and methods to contribute. For example, let's just look at this diagram again, right? For CMI modeling, that's basically modeling the superstructure, right? We have methods that can optimize, find the optimal pathway from a superstructure. That superstructure needs to represent current and future technologies. Today, such models are simply not available, particularly in the public domain. The models that are available are behind paywalls, very difficult to get to. So this is something that we are in the process of developing right now, and we are planning to make our model available for free for non-commercial use. The paper is under preparation right now, so I'm hoping that by the end of the year or early next year, it'll be published and everything will be available, for everyone to use and accelerate the work in this area, in a few months. For figuring out trade-offs, that's basically also an optimization problem, but it's multiple objectives, and it's a high-dimensional space. We need to look at sustainability, circularity, resilience, and other types of factors. For figuring out roadmaps, we have approached it as a long-term planning problem. There's a lot of work, again, that we have done. We have techniques from planning, scheduling. We can look at moving horizon types of approaches. There are deep uncertainties in here. And of course, there are dynamics. Okay, the climate is changing. Technologies are changing. How does one model those? How does one incorporate that? Many of the dynamics have non-linearities, and there are tipping points in there as well. For improvement, there are debottlenecking methods that we have developed. There are hotspot analysis techniques that are also relevant. Innovation. How do we find innovation? How do we encourage innovation? That's also a very important and challenging area. A lot of room here for machine learning types of approaches, for extracting knowledge, for doing molecular design, for identifying reaction networks, and for finding the best reaction pathways. overall, this problem is sort of a very large-scale feedback control problem, which involves integrated design and operation and nonlinear dynamics. These are all areas that PSE has addressed, but at a much smaller scale. The challenge is to now go to this larger scale and address these problems, but in collaboration with the stakeholders. That's very important. Otherwise, we will find ourselves barking at the wrong tree. So I want to now just, in the last several minutes, go to this other area. I've mainly been focusing on net zero emissions. I also want to talk about these nature positive decisions and how PSE can contribute to that and what are the potential benefits of that. Okay. So in this area, what we have been working on in my group is trying to sort of understand how does industry depend on nature. Okay. And we know that ecosystems are the source of goods like water, minerals, biomass, etc. And nature is also the sink for our industrial wastes to the air, to the water, to the land. And there are a large number of ecosystem services that industrial activities and human activities depend on. Things like regulating the quality of the air and the water, getting food, providing water, regulating the climate, the weather, etc. So we have been developing this framework that we call techno-ecological synergy for about the last 10 years. The idea here is that we explicitly want to account for the role of ecological systems and how they support industrial or more broadly human activities. So if we think about trees, for example, they of course take up carbon dioxide and do carbon sequestration, but trees also take up other air emissions like sulfur and nitrogen oxides and particulate matter. And they therefore clean the air. They provide oxygen. They can provide biomass. They also provide many co-benefits to society, such as providing water, recreational opportunities, and so on. Similarly, wetlands can also clean up polluted water, okay, and provide other benefits like flood regulation, can provide food, things like rice grow in wetlands, and, aesthetic value also comes from wetlands and things like that. Traditionally, in engineering, for at least the last 300 years, we have ignored nature. We have taken nature for granted. We have assumed it to be essentially an infinite source and an infinite sink. And maybe that is why we have such substantial degradation of ecological systems. It's not just engineering that has ignored nature. Virtually every discipline except ecology has ignored nature for at least the last 300 years. That's a longer conversation. We can talk about that later on if you're interested. So this framework of techno-ecological synergy, the idea is that we have technological systems. This could be a single process. It could be a supply chain, raw materials coming in, products being made, and wastes being produced. There's a lot of work on trying to, do industrial symbiosis or do circular economy to try and improve, the efficiency of our system, improve its efficiency, reduce its environmental impact. In techno-ecological synergy, what we are trying to do is to explicitly include the role of ecological systems because they can also take up wastes and provide resources. And eventually, just as the way it is in a pristine ecosystem, if there is one like that, eventually we could get to a system that looks like this, where the ecological and the technological system at the global scale is, truly synergistic and self-sustaining, and therefore sustainable. So, we've done a large number of applications for this. I don't have time to get into applications. Most of the applications are published, but some of the applications we have done, is to, show how a biodiesel factory can benefit from vegetation and treatment wetlands next to the facility. This study was done for a facility in Ohio, near Cincinnati, basically. We've also done studies on non-chemical kinds of systems where we have looked at a house and how ecosystems in the yard of the house, this is a typical American single-family house, how planting trees in the yard and improving the efficiency of appliances and changing the thermostat settings can give you win-win solutions that are able to save you money and be environmentally superior. So large number of applications. I've listed some of them over here. I'm not going to get into these in any kind of detail, as I said, but some of the ones that are, I think, very interesting and relevant to PSE Is this application to a chlor-alkali process where we are addressing this problem as an integrated design and operations problem? There's work on supply chain management of corn ethanol for reducing runoff of nutrients that go into lakes and rivers and the ocean to result in harmful algal blooms. We have also done work on the unit commitment problem for power generation. And we have included ecosystem services in life cycle assessment, where these methods basically account for the ecological carrying capacity. And there are new types of metrics that we have developed for absolute environmental sustainability that are science-based, as opposed to many other metrics that are very subjective. Overall, what we are finding, from this work is that, there are a lot of opportunities if we were to include ecosystems in engineering design, okay, and decision-making. We have treated ecosystems just like unit operations, just like another piece of equipment. We've even developed ChemCAD modules for wetlands and trees, so that if you want to add a wetland or vegetation along with your heat exchanger and reactor and distillation column, you can do that. This work is published in Computers and Chemical Engineering. So by including ecosystems, what we are finding is that we're able to expand the design space. So let's consider the environmental impact versus cost, and here is the Pareto curve of the trade-off. This is the space of conventional designs, and this side is not attainable with the current technology. If we include ecosystems in our design, what we are finding for virtually every single example that we have done is that we can expand the design space, and this additional design space, this green region, becomes available due to a techno-ecological synergy. So this space is a space of innovation. And these are innovations that cannot be found by a traditional engineering technocentric approach. Many of these solutions can be win-win. Okay. And we are able to quantify ecological overshoot and encourage ecosystem protection and restoration. Of course, this area is not without its challenges. One practical challenge is that, many times these kinds of, techno-ecological synergies are difficult for a company to justify because the cost is often borne by the restorer of ecosystems on their land, but the benefit is to everyone. So it creates a positive externality. And if only one entity is going to pay for it and everybody else benefits, that sometimes is challenging. So there needs to be some type of incentive policy, government, or consumer, input into that. The other problem that we have realized is that engineers are actually quite ecologically illiterate. And ecological literacy is important and essential for doing this type of work. So we need to educate ourselves about nature and its dynamics and its role. And maybe a simple way of getting started is just look outside your window and try to identify the local plants and insects and birds that you probably see every single day. Lots of PSC challenges in this field. I mentioned integrated design and control. There are nonlinear dynamics. There is spatio-temporal optimization problems here. It's a highly multi-scale type of a system. But if we are able to seek synergies with nature and come up with nature-positive designs, there are huge opportunities. According to the World Economic Forum, by 2030, these kinds of designs are expected to result in $10 trillion of business opportunities and create 395 million jobs. The train has already left the station. Many companies are already establishing research or groups within their company to focus on identifying such opportunities for synergies and benefit from them. So to conclude then, urgent solutions are needed for addressing the challenges that we face in the world today. Climate change, ecological degradation, social inequities. These are some of the major challenges of our time. Corporations and nations have pledged to address these challenges, but making pledges is one thing. They don't have methods and models and tools to solve and address these challenges yet. Small tweaks to the existing system, like increasing efficiency, which is what reductionist engineering is very good at, right? That's not going to be enough. Using renewable energy, I showed you, even for the grocery bags problem, just renewable energy alone doesn't do it. And I did not even talk about the side effects of renewable energy, okay? Reducing life cycle impact alone, not enough. What we need, it seems to me, is we need reinvention of the chemicals and materials industries to a sustainable and circular enterprise. This needs a lot of PSC input and work. Becoming nature positive also requires shifting the entire engineering paradigm to accounting for nature and respecting its limits from the current paradigm that ignores nature and considers its limits to be, infinite. PSC, in my opinion, is a unique position to contribute by providing these methods, models, and tools to guide this transition. But we must expand the system boundary to the economy, society, and biosphere, and we have got to collaborate with expertise in that area. Okay, we have to do deep integration with the other domains. Only then we are going to have lasting impact. Very importantly, education needs to integrate sustainability throughout the curriculum. This is essential, for the goals and for these challenges to be addressed. So let me finish up by acknowledging a whole bunch of graduate students who have contributed to this, collaborators at ASU and other places, and financial support from various agencies. And if there is time for questions, I'm happy to answer them now or later on. You're welcome to send me an email, and I'll be happy to respond in that way as well. Thank you very much for your attention.
Wow. Well, thank you. Thank you for that presentation and overview. We do have some questions here. I've received a few that are available already on the chat. And also I have a couple additional questions as well. One just to start with, we know that there's less inclination towards PSE in some of the young engineers, and some companies are really struggling to find those with experience in modeling optimization, some of these other methods that you mentioned. Can you talk about, it seems like this is an area that a lot of young people are interested in, and what could be the role of, this message toward motivating students towards PSE?
No, that's a great question. It's a very important question and something that we should all be, concerned about and try to address. I mean, I think, to attract the younger generation, what we need to do is to communicate the need and the excitement and the opportunity that PSE and these kinds of methods, can play in addressing the big challenges that we face today. Right. I mean, if people think about, I'm just going to go to a company and basically continue doing things the way they have been done for all this time. I mean, that's not very interesting and exciting to a lot of people, especially the younger people today who have, climate anxiety, among other things. Right. So if we were to focus on sustainability as the goal, right, focus on, chemical engineering for sustainable chemicals and materials, I think that would be a much more effective way of attracting the younger generation. And, those who are more mathematically and computationally inclined in that case will come to work in the kind of areas that I'm talking about. I mean, it's something that I think all of us need to contribute, to doing. And of course, we have to be careful not to greenwash and just talk about it. We also need to modify our education curriculum to incorporate these sorts of things in it. There's a lot to be done there, but I think the opportunity very much exists and the need for doing this is now.
Fantastic. Well, great answer. Another question here, given the ongoing emphasis on sustainable energy, how do you envision the role of nuclear power in the future energy mix? And what are the technological or regulatory challenges that PSE can address to expand its usage?
Yeah, so I get this question often. I mean, nuclear power, I mean, from a carbon dioxide point of view, does have its benefits, no doubt about that. But regulatory policy and societal sort of responses have not been exactly, very good. So if, I mean, I mentioned we need this superstructure CMI model, right? And we need to include all of the alternatives within that, renewable energy, conventional energy sources, also nuclear power. And we can see, what are the trade-offs, of including nuclear energy. Okay. And, I mean, we are in the process, as I told you, of developing this kind of a model, and we are including nuclear power in that also. Nuclear power does not always get selected because many renewable energies, from at least a carbon point of view, do have benefits even over nuclear power. But what PSE can do is provide systematic ways of doing a proper scientific evaluation of that alternative along with all the others, as opposed to sticking with one solution and thinking it's going to be a silver bullet. There are no silver bullets, not for this problem. That's pretty much a guarantee. Okay, second law of thermodynamics will tell you that. And I can say more about this later on if there is time and interest. So I think we need to have these methods and tools where all of these alternatives can be included, and that may also then be used to educate policymakers and the general public. It's a slow process, but it may be better than spraying iron oxide into the ocean or sulfur dioxide into the stratosphere for addressing problems like climate change.
Okay, fantastic. I have another question here. Aurora is excited about all the challenges you've highlighted and how PSE can contribute to those. Hopefully, it's not too late to address these problems. She'd like to know your opinion on consumer behavior. Do you think outreach, education, and policy could help with this? Should these aspects be included in our PSE efforts?
So it is not too late, that's for sure. Okay, although every day is later than the previous day, but it is not too late. There is still a lot of opportunity, a lot of need, so we have got to go at it, with full force. As far as consumer behavior and things like that are concerned, of course, those matter, right? And given assuming that you have an engineering background, like me, I think consumer behavior is the most difficult problem, right? So what we are doing is working with behavioral scientists. And the behavioral scientists do their thing and give us data and models that then we include within our PSE types of approaches. Okay, so that way we can account for the effect of consumer behavior. We can also, realize that there is going to be a diversity of behaviors, and accordingly, the technologies, how they are developed and how they are implemented, can be, adapted according to how the local community or overall consumers are going to behave. So with the right kind of collaborators, I think that can also very much be and should be included within the PSE type of formulation. But collaboration is key. This is not something that most of us, I think, would be able to do purely by ourselves.
Fantastic. Some people look at countries like Germany, and some of the issues they've had with that transition, electrification, using renewable energy. Also, New Zealand has very aggressive targets towards that. There are countries and states in the United States that have been leading, and people have seen some of the problems, but also opportunities. So we're not just dealing with a hypothetical situation. We have data now. How can we use that data within PSE to help design the next country's transition or the next state's transition to avoid some of those problems that we've seen on the other ones?
No, great question. So let's think about how have these companies made these countries rather, made the decisions about, like we said, Germany decided to completely get rid of nuclear, right? France has had these yellow vest protests, and there have been cases, New Zealand has very aggressive goals, and so on. Here in the US, California has much more aggressive goals as compared to other parts of the country, and so on. How are these kinds of decisions being made? How is that roadmap, if there is one, being developed? Okay. Today, the way most of this kind of work is done, to the best of my knowledge, is they get a bunch of experts into a room, and they come up with a plan, with a roadmap. Do they have systematic methods and models and software tools that can actually develop the roadmaps based on the best scientific knowledge that we have? That actually account for the emerging technologies, and they account for, social and consumer pushback. Okay, that account for the effect on profitability of companies and potential pushback from that. So what we need really are these kinds of systematic methods and tools. And, if we approach this with such tools, then we know that this is not a problem that we're going to solve overnight. It is not a solution that we will figure out and we just stick with it and everything will be fine. It's a problem that involves continuous control, continuous feedback control, if you like, right? Adaptive management, if you prefer. So we need to repeatedly, as we get feedback, okay, we tried something, it didn't work, there was pushback. Okay, we come back and redo our planning problem, right? And we find out another set of solutions. And then we try to implement those. So to be able to do this, we need to be able to, have more than just so-called experts to focus on it. We need these systematic methods, which is what PSC has done really well, but in a narrow domain. We need to go to the larger domain now.
Well, I think that highlights your message even more. We need a data-driven approach toward making these decisions, and PSC holds a lot of those answers to guide strategy. Another question from Leonard. This is a very interesting presentation. I'd like to know what would be the first step in implementing PSC tools in a subject focused on chemical process simulation in a way that includes this topic of sustainability. Perhaps there's a book reference that could be shared to explore more on this topic.
Yeah, that's a good question. I mean, so I'll give you obviously my biased view, right? So if you look at some of the work that we have been doing, I think those are some of the first steps. Okay, I showed you this framework for this net zero emissions, right? So the first step is the model, a model of the chemical industry. Okay, today, as I said, there is no model that is available that people in academia can use without paying a hefty fee. Okay, so the first thing is to develop that kind of a model, right? Once we have such a model, or maybe you don't want to look at the entire industry, you just want to focus on, say one type of product or one type of industry. Okay, say you're only interested in ethylene or polyethylene. Okay, so we need to start out with that model. Then we need to figure out what are the alternatives and come up with models of the alternatives. We need to understand what is the status of the alternatives? Are they available for commercialization today? What is likely to be their evolution, for commercialization in the future? And then, find the solution and the roadmap to that. There are technical papers on this. I've written a textbook on sustainable engineering. It doesn't quite get into the nitty-gritty of these kinds of aspects because the book is written more for an undergraduate, first-year graduate chemical engineering type of an audience, and this work, wasn't quite there when I was writing the book. But I'm happy to discuss this in more detail if you like. So hopefully I'm answering your question in the way that you had intended.
Well, fantastic. I've included a link to your textbook in the chat for those that would like to see that textbook and learn a little bit more. Well, we are out of time now. Thank you so much for your presentation. Very insightful. And also congratulations as well on your award, the AIChE Cass Division Computing in Chemical Engineering Award. It's well-deserved. And your message about sustainability and having that paradigm shift from profitability to something more broad, includes sustainability in the future within process systems engineering is well received. So thank you so much for that message, and I appreciate your time that you took to prepare this presentation.
Yep. Thank you, John. Thanks to the CAS division, and thanks to all of you who have participated.
Okay. Well, thank you, everybody. Appreciate your questions as well. We will post a copy of this after this presentation to YouTube.